Okay, hello, this is July 22nd, and we are now going to cover chapter 15 of the book on physics 122. Chapter 15 is just the other three laws of thermodynamics. We have already covered the zero law of thermodynamics. We also covered this new idea that is the temperature and the amount of substance, that's the mole. This concept here is related to the number of Avogadro. What we are going to do today is to cover the first law. What we are going to do in this recording is first to cover the first law of thermodynamics. Okay, and just as a heads up, what we are going to do here in this chapter alone, you don't have to study everything. Here you go. Let's what you have to worry about this chapter is going to be 15.1. 15.2 is an important section of the book and is somewhat easy to understand. 15.3, 15.4, and 15.9. We're going to skip 8, 7, 6, and 5. Those 5, 6, and 7, and 8, they're more difficult, so I would leave that for a more advanced course, okay? So again, section 15.1, 15.2, 3, 4, and 9. I'm going to document here for you. That's the material that you have to worry about this chapter. In chapter, concentrate on the following sessions. Point 1, 2, 3, 4, and 15.9. Okay, 15.1, just gonna document for you here, is the first law of thermodynamics. 15.2 is thermodynamic processes. Thermodynamic processes. And what do I mean about that? Basically is known as the PV diagram, the very important diagram. It's important and it's not that difficult to understand. Okay, that's what is nice. It's very productive to cover something like that. 15.3, thermodynamic processes for an ideal gas. So what we're going to do, whatever genetic concept was presented here on 15.2, we will apply that for an ideal gas. 15.4 is reversible and irreversible processes. And 15.9, the third law of thermodynamics. Those what you have to worry about this course. Let me just give you make a little brief about the other chapters. Okay, 15.5 is applied to internal combustion engines, for instance. Okay, so it's important, but I prefer to leave it for a more advanced course. Then we have refrigerators and heat pumps. If you want to understand how air conditioner units and refrigerators work, That's where you have to go. Okay. I was buying a air conditioning there in Brazil air conditioning unit there in Brazil, and I want to know how it works, how air conditioning works. So I went through this theory of the functioning of air conditioning. Is pretty interesting. Okay, it uses all those concepts in thermodynamics, reversible engine and heat pumps. Okay, it's applicable to the other ones. Entropy, and then the entropy, the concept of order. Okay, I think that those sections are a little bit advanced, so I don't usually cover in my courses. But the other ones are more productive to do. Okay, so let's concentrate on those. Let's get back here to our chapter. Let's start with the first law of thermodynamics first, right? Here you go. So we have all the basic quantities, going back to the building blocks, right? We have the basic quantities, we have the primary definitions, and you have the laws of physics. So we already talked about the 4 laws of physics in mechanics. We talked about the 0 law of thermodynamics. And we are going to cover now the first law of thermodynamics. There are 2 more. Just to remind you what the first 0 law of thermodynamics is all about. Don't forget, those are core concepts, right? All those 3 things are the beginning of physics. Oh, let's say the beginning of physics is those 2. And the laws of physics come after those 2. None of those 3 concepts can be derived mathematically. None of those 3 concepts can be derived mathematically. What we have here, depending on the scientist's imagination, and also what works better to explain the universe, including the primary definitions, and then the laws of physics, we obtain from the other 2 by doing experimentation. Okay? So consider 0 law of thermodynamics. Just to remind you, right? We already covered that. Consider 3 objects, A, B, and C. If A is in thermal equilibrium with B, and B is separately in thermal equilibrium with C, then A must be in thermal equilibrium with C as well. Okay? So what about the first law of thermodynamics? The first law of thermodynamics is a mathematical equation. Is a mathematical equation. Okay. This law relates, when I express the internal energy of a system, with the heat that is either input or output from the system. From the system, and the work that is done on the system. Okay, you have to understand how you calculate those quantities. The heat usually is given to you, what the value of the heat is put in the system. But the work, is something that you have to calculate. Usually you have to calculate. I'm going to explain to you what's work done on the system. So the law is expressed in the following way. I'm going to express it in the notation of the book. So if you need to refer to the book, you use it. Okay, so here you go. The law is expressed in the following way. The change in internal energy. Here you go. The book refer to the change in internal energy as U, delta U. Other books out there, here you go, other books out there, refers to the change of internal, the notation that they use, the notation of other books refer to the change in internal energy as delta E internal. Okay, that's what other books state. So in the case of the delta U here in the book, he's using that notation to remind you of the change in potential energy of the system. And that's exactly what the internal energy of the system is all about. Is a type of potential energy. The potential energy can be a chemical potential energy, can be a nuclear potential energy, okay? Doesn't have to be necessarily the gravitational potential energy. And then what goes in the next, in the right side, is Q plus W. And I'm going to be very specific what this W is all about. Something wrong here. Interesting. Q plus W. I'm going to be specific that the W that we're talking about is the work on the system. Okay? That's what we have here. This W here is the work done on the system. There are two ways to express this equation. Either for the work done on the system or the work done by the system. One thing is different from the other. Okay? Although one has the same magnitude of the other. Okay? So another way to express this law, is by rewriting it in the following way. By the system, work done by the system, but then you change the sign because the work done by the system is equal to minus the work done on the system. Okay, so we can write that down like that. And I'm going to illustrate what exactly that means. It's usually, easier to solve the problem if you calculate the work done by the system. Okay? So that's the relation. Let me give you an example. How it goes. Example of how to calculate the work on a system. Okay? So, example, consider an internal combustion engine installed in a locomotive. Okay? Let's do even better. Installing a car, just your regular car. What's the mass of regular cars? Let's take a look here at the internet. Mass of regular cars. Just like my Honda Civic, right? Mass of a Honda Civic. Honda Civic is one of the smallest cars that we have out there. It's a very simple car too. Very reliable, right? It's around 1,000 kilograms. 2,000 pounds, okay? So let's give an example of how to calculate the work on / by the /A system. Consider internal combustion engine installed in a car as being your system. Okay. This engine propels a 1,000 kilogram car from rest to 10 meters per second. Is that a lot? 10 meters per second. 10 meters per second is what? Is 600 meters per minute, right? 600 meters per minute is 0.6 kilometers per minute. Yeah, it's pretty good, not bad. So 0.600 kilometers per minute is what? 36 kilometers an hour. Not bad. Something around 20 miles an hour is not too much. Propels a 1,000 kilogram car from rest to 10 meters per second over a distance of, let's say, 500 meters. Okay. Find the work done by this engine and then determine the work done on the engine. Okay? Very simple problem, so you can understand how to solve for different problems. We go ahead and let's see here, illustration, right? We go ahead and calculate the we come up with an illustration first, right? Let's go. I'm going to go to the last slide here. And then I'm going to go back to the syringe that you see in there. So the situation is the following. Here's the car. You know, we have an engine there installed in the car. Right in here. That's the engine. Okay. Good. The initial velocity of the car is initially at rest. Let's put that here. V is 0. V naught is 0. And later on, after it moved a given distance, you have a final velocity of 10 meters per second. We have solved this problem before in Physics 120. Okay. We have solved this problem before in Physics 120, right? You move 500 meters. Let's go back to the drawing here. front of the car to the front of the car. No. Here you go. So this engine is providing a force to the car like that. That's the force that the engine is applying to the car. So it is as though the force of this engine doing a work on the car, right? Because that's how you have to picture that force that the engine is applying to the car. Here you go. Force right in here. Let's see if I can get it thicker. Wait, like that. The distance is 500 meters. Meters right in here. You must be kidding me, right? There you go. We're assuming that the force is constant. Assume that the force is constant. That's the easy one, right? That's the easy one to solve because we already did that in physics 120. Consider an internal combustion engine installed in a car as being your system. This engine propels a car, a 1,000 kilogram car with a constant force from rest to 10 meters per second over a distance of 500 meters. Find the work done by this engine and then determine the work done on the engine. Yep. By the engine. It's easier to calculate the work done by the engine first. Okay? And then we just use this relation here. The work done by the engine, we can find the work done by the engine using the work kinetic energy theorem we saw in P120. Remember that theorem is the difference in kinetic energy. Work done by the net force, right? Actually, the work done by the net force, which is going to be the final kinetic energy minus the initial kinetic energy. Final kinetic energy minus the initial kinetic energy. The initial kinetic energy is 0 because the initial velocity is 0. The final kinetic energy is half mv squared, half mv final square can calculate here using my software, right? Oh yeah, here you go. I already have part of it. Let's do that. mv squared, and the mass is 1,000 kilograms. The velocity is 10 meters per second. I don't need the calculate everything. You go. We get that 50,000 joules or 50 kilojoules. What you have here is joules, the unit of joules. Okay. $50,000 joules. 50,000 joules. So that's one example of how you can find the work done by a system. Okay. Oh, and by the way, what is the, let's see here. And the work done on a system, right? Would be the negative of that. On the engine. That's one of, that's one type of problem that I'm gonna find out there. Okay, so what does it mean that the work done on the system? What does it mean that the work done on the system is negative? Okay, what does it mean? You gotta start thinking about the interpretation of what you see in there. Okay, the meaning is the following. It means that the system lost internal energy, or lost internal or potential, okay, or potential energy. That's what it means. That's what it means. If the work done on the system was positive, if the work done on the system was positive, then it means that your system gained potential energy. Okay? That's what it means. An engine, while it's running, it usually loses potential energy, or potential energy that's stored in the fuel of the engine. Okay? An engine, when it is working, loses internal energy because it is burning its fuel. The actual energy is in the fuel itself. When you fill up the tank of your car, okay, what you're doing, you are adding potential or internal, all right, or internal energy to your engine. Make sense? So the fuel has the potential energy, and it is the engine that knows how to use that potential energy. It's the engine that knows how to unlock that potential energy and convert it into something useful. Okay? The potential energy is in reality in the fuel of the car. We can So if we go back here to this law of thermodynamics, every time that the work on the system is negative, here you go, what's happening to the internal energy? Assuming that this guy is zero, right? Assuming that the heat is zero, we're losing potential energy. That's what this equation is telling us. Every time that the work on a system is negative, the system is losing potential energy. Similarly, if we add heat to the system, something interesting happens. The internal energy increases. So heat can be used to increase the potential energy of a system. This is a very simple equation. And it's a law of physics. It's a very important law of physics. Okay, so let's document, right? Let's further investigate the above law. Further of the above law. Okay? If Q is equal, so we have the following situations. We have the following situations. One, Q equal to 0 and W1 greater than 0. That's one possibility, right? Internal energy of the system increases. Example. When you fuel your car at the gas station, okay? You're not adding any heat to the system, you're not subtracting any heat to the system, you're just adding fuel there to your car. That's one possibility. Here you go. The other possibility is heat equal to 0, but now the work on the system is negative. Internal energy of the system decreases. Example, when you burn the fuel of your car, either way, when you burn the fuel of your car, either in the freeway, on the freeway, or when your car is idling. If your car is idling, the engine is not doing any work whatsoever. The work done by the engine is 0, so you're just wasting fuel. And you're decreasing the internal potential energy of your car. Okay? So what are other possible conditions here? Heat greater than 0, equal to 0. Internal of the system, of the energy of your system increases. Okay? When you warm up, let's say, the water in the stove, okay? The water internal energy increases. Can you picture that? And then if you're smart enough, you might be able to extract that hot energy from the water. At the beginning of the Industrial Revolution, people would do that. Instead of having an engine that consumed gasoline, they used to have water that was heated, and it was what they called a steam engine, right? Internal of the energy increases. In the stove, the water internal energy increases. the work done on the water is going to be zero because the water doesn't expand, doesn't contract. Okay? We're just warming the liquid water. I'm not boiling it. And then we have this other situation. Again, example, when you cool down, warm up the water, when you cool down the water, when you cool down the water, cool down the warm water in the refrigerator, the water internal energy decreases. So, and then you have some other situations too, right? You can have both of them different of zero, right? We also have this situation here. Here you go. Internal energy of the system increases, right? I'm not going to give an example in this case. We can have a situation in which the work is negative. Here you go. And there's another condition, and magnitude of Q, no, not magnitude, Q is greater than magnitude of the work done on this system. The internal energy of the system increases as well. So when you subtract this number from Q, you still get a positive change in internal energy, right? We have this other situation, let's say. We have greater than zero, but now the work done on the system, the magnitude of the work done on the system is more than Q. The internal energy of the system decreases. And finally, you have the other case. Total of how many? Let's see. We have a total of 10 cases that you're going to find out there. It all depends. Okay. Let's see. Here you go. If both the Q, the heat is less than zero and the work done is less than zero, in terms of the energy of the system decreases. Okay. Here you go. We can have the situation in which the work done on the system is greater than zero. And what else? Now the situation reverts here. Work done on the system is greater than the magnitude of the heat internal energy of the system increases, right? What else we have here? We must have all sorts of combinations, right? We can have Q equal to 0, W equal to 0, and then you have situations and Q and W are different of 0. Okay, so here you go. Q greater than 0, W less than 0. But now the Q is greater than 0, so the internal energy of the system increases. On the other hand, it decreases. Now, what about the other way? Q less than 0, and work done on the system is negative. That's decreased, definitely, because that sum that you saw there is going to be a negative number. okay, then you can also have work done on the system is greater than 0. And in this case, the internal energy is going to increase. And what's the other one? Let's see, we must have, let's see here. I think I covered everything, right? So those are the 10 possibilities that you're going to see out there for this equation. It all depends on how, you can have Q equal to 0 or W equal to 0. And if the internal energy increase or decrease in those situations, it's going to depend who has a negative or positive sign, right? And then you have things a little bit more involved, right? Both of them are different of 0, but depending on their magnitude, the internal energy can increase or can decrease. So those are the possibilities that I'm going to see in there for this equation. Now let's look differently. How we can calculate the work done on a given system. A very good way of visualizing a thermodynamic system is like a system like that in which you have a gas inside the container and has a piston that can go back and forth. Okay? Think about this piston as your engine, your gasoline vapor inside your car piston. Every car, every internal combustion engine has a piston where the fuel is injected on the inside. And you have this piston that moves back and forth. Okay? So the gasoline inside this piston, when it is ignited, it behaves like a gas. And then it's a question of finding out whether the work done on the system is going to be positive or negative. Okay? So there is a very simple way of recognizing whether a gas in a system like this one with a cylinder and a piston is doing positive work or negative work. Okay? So think about that, the system is the gas. When you're talking about work done on a system, what does it mean? It means that the work done by the outside system, by what is outside the system. Work done by the environment. Do you see how it works? So there are more than 2 ways of picturing this type of problem. Let's go take a look here. Here you go. Not only you can say that the work done on the system, but also the work done by the system, right? That's one way of looking at the problem. But there is also the work done on the system by the environment, and the work done by the system on the environment. So you have this other way of looking at. Okay, so here you go. Work done on the system. Is if we say the work so work done on the system means what? Work done on the system in the environment. That's what it means. Work done on the system. So work done on the system, if the work done by the system is on the system is X, then work done by the environment is minus X. Okay? So and how do we picture that? Here you go. If a gas is expanding like this one right here, is gaining space, right? So we say that the work done by the system is positive. and the work done on the environment, which is becoming smaller, is negative. That's the case here. In this case here, the work done on the system by the environment is positive because the environment is expanding, whereas the system is decreasing. So the work done by the system or by the gas is negative. Okay? So let's go back here. Consider the case. Consider now the case of a cylinder with a gas of a cylinder and a piston with a gas inside it. We can erase that. If a gas expands its volume and takes over the volume that once belonged to the environment, belong to the surrounding environment, we say that the work done by the system is positive and the work done by the environment is negative. Okay? Volume, here you go. One, if a gas expands volume, it takes over the volume that once belonged to the surrounding environment. We then say that the work done by the system is positive and the work done by the environment is negative. On the other hand, if the gas contracts, the gas volume decreases, it means that the volume of the environment of the surrounding environment increases. We then say that the work done by the environment is positive and the work done by the gas is negative. Okay? So here you go. Let's go here to my example of the syringe, right? Or even, which is the case of the piston. What you see right here is the case of a piston, a cylinder of a car, of internal combustion car. Okay, here's the cylinder, and here's the piston. Okay? And I'm going to do something else too. I'm going to cap this little guy here. I'm going to cap it so no gas escape my system. Here you go. Send to back, right in there. The situation is similar, by the way, okay? Here you go. Capped. Bring to the front. Bring to front. And I'm going to do even better. I'm going to increase the transparency of this guy so oh, that's not what I want. That's not this transparency I want. I want. Here you go. Okay? Oh. I'm going to put that at the bottom. Cylinder, gas inside a cylinder with a piston. Okay, so let's say we start at this volume and then we compress the gas. The piston is compressed. Okay. Internal energy of this gas increases. That's what it means. The work done on this system is positive. I'm assuming that heat is equal to 0, okay? Heat is equal to 0. Symbol. Like that. Let's go for the next one. Now the opposite. Let's do the opposite. Now I want to switch sides, right? This guy here is going to start at a smaller volume, and the gas is going to expand. Here you go. Gas inside the cylinder expands. It loses internal energy because the work done on the system is negative. Work done on the system is negative. So it's just a matter of understanding what work done on a system means. Like that. Here you go. Like that. That's what you have to know about work done on a system. It's very simple. Doesn't get more complicated than that. Okay, let's take a look at this example here. It's an interesting example here. So here you go, the case of someone that's working out in a elliptical trainer for 30 minutes. Okay, so during the workout, Katie, right, is pushing the machine with her feet at an average rate of 220 watts or joules per second. She is applying a force, right, and she's displacing the machine as she does the workout. Heat flows from her body in the surroundings by evaporation. So every time that we work out on the street, we are losing heat. Okay? In this case, it's going to be by evaporation, convection, and radiation. The human body radiates energy. But because there is evaporation going on, we also have convection. Heat is being transferred by convection and radiation. Okay, and the average, you don't have to know how much by evaporation, you don't have to know by how much by convection, you do not know how much is by radiation. Those are ways of transferring heat that we saw, right? And the average rate is 910 watts, 910 joules per second. What's the change in internal energy? What's the rate of the right way of putting this question? What is the rate of change in her internal energy? Okay, that should be the right way of asking this question, rate of change in her internal energy. She's losing internal energy. The muscles is losing internal energy. And she's doing work on the outside. It's losing internal energy by heat and also by doing work on the environment. That's what she's doing. The environment is not doing work on her. Okay? So here you go. All you gotta do is to apply thermodynamics first law of thermodynamics. Q plus W. She's losing heat. Consequently, the rate of losing heat is negative. That's why they put it here, the negative sign here. She's also doing work on the system, right? Here you go. That's the work on the system, right? That's the work. The heat is this part here. She's losing heat. We have the negative sign here. She's doing work, on the environment, or the work done on the system is negative. So we get this rate of loss of internal energy or potential energy, 1130 joules per second. During a 30-minute workout, if she's doing that constantly at a constant rate, it doesn't change the effort during the workout, then all you gotta do is to multiply this value here by 30 minutes. 30 minutes times 60 seconds. And we end up getting 2 megajoules. Okay? One serving of pasta applies 1 megajoule of internal energy. How many servings of pasta would supply enough internal energy for the workout? Okay. So if she lost 2 megajoules during her workout, all she needs is 2 servings of pasta to make up for the loss of energy. But that's just a rough calculation, okay? That's just a rough calculation. In reality, it's not exactly 2 servings. It's a little bit less, because not the total of 1 megajoule is used for the workout. It's used for the other things as well. Okay, so that's what we have for the first law of thermodynamics. Okay, so I'm going to pause it right now, and I'm going to post this video alone there in the website.